My name is Günter Leugering. It's my pleasure to introduce to you Professor Enrique Zuazua from BCAM. BCAM stands for Basque Center for Applied Mathematics, that in fact was founded by himself and Iker Basque in 2008. Let me say some words about his career. So Enrique Zuazua studied mathematics at the University of the Basque Country and did a sandwich PhD, so to speak, with this university, and Paris 6 were under the advice of Alain Hérault, and I understand also under the advice of Jacques-Louis Lyons, in a sense. From there, this was in 1988, and meanwhile he had an associate professorship at the University of the Basque Country, and then at the University Autónoma in Madrid for 2 years. From there he went to a full professorship at Complutense in Madrid until 2001, and then he moved to Autónoma again, and from there he took off to Basque Country again to found BCAM, where he is now a research professor ever since. Enrique Zuazua has also visited a number of important places, and I don't want to steal his time to go through all of them, right? Let me mention Courant Institute, let me mention Newton Institute, and many, many others. He has received a variety of awards, and prizes. And most notably, maybe, and most recently, the Alexander von Humboldt Prize award that is awarded to him in 2013. And by the end of the week, he will attend a reception in Bamberg about this. He has also been involved in the French Excellence Initiative, where he has a semi-excellence professorship in Toulouse last year. Also, he was awarded with the Doctor Honoris Causa by the University of Nancy. He received national prizes, a prize by the royals of Spain, Julio Rey Pastor, prize, a very important prize also. Well, I don't want to talk about his administrative things and that he did in his life. He has written a number of papers that is almost intimidating, so at least the lower bound, as I should say, is 230, maybe 250 now. I checked only last week, so maybe. So he has written a number of books and is editor of many, many journals. And so, coming to the scientific part, his major fields of interest are optimal control, controllability, stabilizability, and PDE analysis, asymptotic analysis, homogenization, and all kinds of things. And what is also very remarkable, at least from my point of view, I like this very much, he's not a person who would sit in his niche and prove theorems only, but rather also he is very involved in dissemination of mathematics. He runs an own broadcast of the TV where he convinced people that mathematics is good to do. We are all glad, Enrique, that you're here, and would like to hear you lecture on optimization of placement of sensors and actuators for waves, please.
Okay, thank you, Günter. I think you have all realized that Günter is also a good friend. Thank you. I realize that the title is a bit too long, but I will try to make my talk to fit into the time schedule. I'm very sorry to start this talk just after I learned that there was this German airplane that crashed from Barcelona to Düsseldorf with 148 people inside. So, okay. I will devote this talk to the memory of all of them, because as the President Hollande said, they don't expect anyone to be alive. Okay, so I think there is no direct flight from Lecce to Bamberg, right?
No, sir.
No, so I don't have any risk. Okay, so this is the topic, optimal placement of sensors and actuators for waves in homogeneous and heterogeneous media. The title is a bit long, but it contains all the key words. So first, some motivation. There are many processes, many issues in different disciplines, sciences, that in a way or another have to do with waves. I have here listed some of them: noise reduction, seismic waves, environment, gas, aeronautics, the human cardiovascular system. Probably when reading this slide, you will say, well, Enrique here is referring to many different issues altogether, and this is true. But I have taken this definition of what a wave is from the book by Witham, and then Witham, the author of these celebrated books back in 74, he said something like this: there appears to be no single precise definition of what exactly constitutes a wave. Various restrictive definitions can be given, but to cover the whole range of wave phenomena, it seems preferable to be guided by the intuitive view that a wave is any recognizable signal that is transferred from one part of the medium to another with a recognizable velocity of propagation. The signal may be any feature of the disturbance. So then I hope you agree that according to this definition, all the motivations I have given to you they fit well. There is a second motivation. So control theory is also a very classical topic. This sentence is taken from the book of Aristoteles. He was, by the time, he had already the intuition that automatics should play a key role in the development of society. And he referred to this issue by saying that if every instrument could accomplish its own work, obeying or anticipating the will of others, if the shuttle whiffed and the peak touched the lyre without a hand to guide them, chief workmen will not need servants nor masters slaves. And 20 centuries later, or even longer, Norbert Wiener defined the concept of cybernetics that was first coined by the French physicist Ampère, saying that cybernetics is the science of control and communication in animals and machines. So when addressing this topic from a mathematical point of view, you are very soon led to manipulate a number of tools. It's hard to work in this subject by simply applying one directional, say, techniques. One has to combine the theory, certainly, of hyperbolic PDEs as the key model for the propagation of waves, control and optimal design theories, of course, and then, as you will see, and this is the goal of my lecture, to try to show you how, in a way or another, even if your goal was not that one, a priori, you are led also to discuss deep issues related with spectral analysis, microlocal analysis, and also from numerical analysis. That will be the end goal of my lecture. So before I go further and to better motivate the spirit of what we are trying to do, let me remind you a very prototypical application of control theory of waves, which is related to noise reduction. So there are there are mainly two ways of reducing noise. One is the passive one. So this is like in this auditorium. This auditorium was designed once, hopefully well, so that the acoustic waves propagate in an accurate manner without obstacles, without resonances, and this very much relies on the carpet, on the isolation of the walls, of the roof, and so on. And then there is also the active approach, the feedback approach, in which there are sensors and actuators playing all the time. So if we are living in this cloud, this is the cloud in which we are, there is some level of noise. There is always some noise left over, right? And then you have to measure it, but you also have to measure the noise that could be coming from the outside, a train or a car or kids playing outside. Then by superposing these two measures, you can have an idea of how much anti-noise you have to apply, right? But of course, in order to do that, you need a math algorithm, and this is what I will try to explain you today. Okay, so this is the simplest example. So this will give you a very basic idea of this intuition by Norbert Wiener that communication and control come together. This is probably the simplest example. This is the D'Alembert equation for for the string of the guitar. The string is vibrating. This is the one-dimensional wave equation, time acceleration equal to curvature. And we are controlling on one of the extremes through this force. Well, it could be the Neumann boundary condition, it will be the same. So V, the only difference of this model with respect to the classical one we teach to students is that there is a non-homogeneous boundary condition, which is actually the control. And we are trying to control the vibrations of the chord of the guitar to 0. This is something we know all how to do, right? We have played all this game, and we know this can be done. But the issue is how to prove that mathematically. If you address this problem from a mathematical point of view, probably the best you can do is, rather than addressing the issue directly, here you could do it, because there are explicit formulas for the solution of the wave equation, like D'Alembert equation, D'Alembert formula, or the Fourier representation. But in general, you don't have access to these explicit formulas, so you better treat the dual problem of observation. So Norbert Wiener said control is equal to communication. So this is the problem of communication. So this time now I take the same wave equation, I change notation, because now phi is denoted the co-state, the adjoint state. There is no control anymore. So these are free waves propagating on this vibrating string. And the question I am now interested on is this problem of observation. So whether a sensor that is located at the extreme x equal 1, by measuring the normal derivative, the tension of the string under vibration, which is fixed. Of course, we all know that there is a connection, because we have experienced this, right? There is a connection between the energy of the vibration and the force you need to apply to keep this boundary condition fixed. Then the question is whether the energy that you are able to record on this extreme x equal 1 during the time interval 0 to capital T, this recorded signal, this recorded energy, is able to recover the full energy inside. Of course, this is also a key issue when dealing with inverse problems in which you have surface measurements as in there, and you try to recover what is underneath. Okay, so in this case, of course, the answer is very simple. This inequality is true if and only if capital T is greater than 2. 2 is the waiting time. You necessarily need to wait to make sure that all waves that are propagating on the medium to the left and to the right, so this is the space interval 0, 1, this is time. So there are waves traveling to the right that will get very soon to the sensor, but there is one, that is the laziest one, that is traveling from nearly the extreme x equal 1, going to the left, bouncing back, and then taking a time which is of the order of 2 to be recorded by the sensor. So in this case, this inequality, which is an observation inequality, is true if and only if T is greater or equal than 2. So you see that using this idea of Norbert Wiener of looking to the dual problem, we have reduced the original control problem to a problem that we, as a PD analyst, we feel much more comfortable with, because it's just a matter of proving inequalities. Right? So now we have to prove this kind of coercive inequality. The normal derivative on the boundary is capable of recovering the full energy of the solution. Of course, this is not true for any smooth function depending on x and t, but we are here working within this class, this linear class of functions that fulfill the other restrictions that the PD is imposing. Right? So for these observation problems, PD solutions are subclasses of smooth functions for which these kind of inequalities are likely to hold because of the qualitative properties that these functions develop because of being the solution of a given PDE. Okay? So this is the point of view. Now, inequalities, we all know how to prove them. There are many different tools, and precisely this will be one of the goals of my lecture. Try to convince you that these inequalities can be proved and try to explain what is inside. Well, there were also a number of attempts in order to make this implicit statement of Norbert Wiener in the definition of cybernetics to make it explicit, precise. And this was, for instance, the contribution of Jacques-Louis Lyons back in 1988. He said, indeed, it's true. If you are able to prove this inequality, and this is something PD analysts like to play with, then you can compute the control. The control is nothing but the normal derivative of a very distinguished solution of the adjoint PDE that you can compute by minimizing a functional in which precisely the quadratic part is the observed energy on the boundary. So this is a nice continuous convex functional in a Hilbert space. The only tricky thing in order to prove that the minimizer is achieved, the one that will lead you to the control, is to prove that the functional is coercive, and the coercivity is precisely equivalent to proving this inequality, which tells you that even though you are observing a very narrow trace of the solution, this, because you are dealing with the solution of this specific model, the wave equation suffices to recover the full energy of the solution. Then you put in this linear part of the functional the initial data y0, y1, you are trying to control. This is quadratic plus linear. You minimize this functional, and when minimizing, the normal derivative you get is precisely the control you were looking for. Then, not only this proves the equivalence, but it also gives you, say, a computational tool in order to build numerical accurate approximations of these controls. Okay, so this was the toy model, D'Alembert equation in 1D. What about multi-D? Well, we all know the acoustic wave equation in multi-D, right? So this is the same model, Laplacian, for the Laplacian in several space variables. Omega can be any bounded nice domain in RD, D, any dimension, but let's think on 2 dimensions. So the question is now the same. Now, rather than dealing with boundary traces, I prefer to simply place the sensor. The sensor will be a patch, right? A recorder I am placing somewhere in this room. And then the question is whether the patch has been well chosen. The location of this patch, the sensor omega, small omega, has been well chosen, so that by, for instance, measuring the kinetic energy inside the small omega, this will give me or not a measure of the total energy of solution. So again, is an inequality for the solutions of the wave equation. You could think on it as an inverse problem in which you are trying to reconstruct the full, say, solution out of measurements done in a small omega. Okay, so this is the drawing. Waves are propagating in this large cavity, this auditorium, in 3D. We have placed, so here I have taken a very thick microphone, right? So this is our microphone. Waves are being recorded here, and I would like to know whether I can reconstruct the energy of all solutions in capital omega. Okay? Now, this problem is not an easy one. So from an analysis point of view, this required a lot of efforts, and the program was somehow completed by Bardos, Lebois, and Rauch back in, I think, 88, based on previous contributions by Ralston, for instance, that developed the construction, the classical geometric optics construction of Gaussian beams. They introduced the so-called the geometric control condition. They said, well, in fact, if you are trying to control the wave equation or proving this inequality for the wave equation, you can ignore the PDE. You can reformulate the problem as a geometric problem. So the geometric problem is very easy to formulate and then hard to solve in practical cases. The geometric condition says, well, the only thing you have to do is look to all possible rays of geometric optics propagating in omega. So you generate the dynamical system associated to the domain omega, the billiard, right? So you take any possible placement of the ball, you kick out this ball in any direction, it will bounce on the boundary again and again and again forever. Then you will be able to control the system or to prove this observation inequality if and only if you make sure that all rays of geometric optics pass through this sensoring region. Of course, and this was already formulated by Ralston, in case you miss any of these rays, you will not be able to do it. Why? Because there are Gaussian beams. These are like Dirac deltas, very oscillatory, narrowly supported Gaussian envelope tubes of waves that are living near this ray, and therefore if this ray doesn't penetrate a small omega, you will never be able to record that part of the energy. This is what Ralston said. And then these other people, they proved the positive formulation of this result. So you see that when going from 1D to multi-D, the principle is the same. waves are driven by rays, right? Waves are driven by rays. And then if you want to control or observe waves, the only thing you have to do is to make sure that your patch, your sensor, is located in a place that is absorbing all these rays, right? Which is now a finite dimensional dynamical system, because it simply depends on the initial location of the support of the ray and the orientation, right? So in this case, this will be 4 dimensions. Okay, so the philosophy is the same, but you see the effect is totally different. So in 1D, of course, rays are simply bouncing back and forth in this interval. This interval is very boring. There is nothing you can do other than walking left or walking right. But when you are in a 2D landscape, right, and this is why we like to live in a 2D surface, right? Some people like hiking, right, to also go into the third direction. So then in 2D there are plenty of possibilities. So you see that, for instance, in a square or rectangular membrane, if you decide to place your patch here or there or there or there, you will never succeed. Why? Because there are trap rays, the vertical ones over there and the horizontal ones over there, that will never get into the region small omega. So this gives you immediately a counterexample of the fact that this kind of inequality, right, even if apparently very simple, is actually hard to achieve in practice, and there is plenty of, say, geometry and dynamical system theory inside. Okay? So this is a typical example of how things can get wrong, right? So you can think on this, say, elliptical cavity where waves are propagating. If for some reason you failed and you had 2 small little holes on this cavity, this will immediately generate a trapped wave. This trapped wave that will be almost impossible to be seen from a classical spectral analysis. Eigenfunctions don't see this kind of trap ray, but there are high-frequency Gaussian beams, tubes of solutions living there. This trap wave will be invisible, for instance, for a sensor which is surrounding the whole, say, exterior boundary. So this is a counterexample showing you how sensitive these inequalities are with respect to the geometry or to the topology. Of course, you can make these holes to be as small as you like in measure. This doesn't really matter. Regardless how small they are, this trap wave is there and therefore will be invisible from the outside world. Okay, so then, well, as you know, control theory is a multidisciplinary topic. We go often to conferences in control engineering. There, the placement of sensors and actuators is a very key topic. People don't only like to know whether a given system is observable or not, but you want to improve the observation properties. You want to know where the sensor should be located. So we thought on, this is a joint work, I think their names are almost invisible, Yannick Privat and Emmanuel Troella in Paris 6. We wanted to formulate this problem in an analytical manner, and this is the way we found to do it. We said, okay, so let's try to address the problem of the optimal location of sensors or controls. I will simply talk about the observation problem because we know the other one is the dual, right? So let me now take again the wave equation in the same cavity. So we are living in this cavity, capital omega, and my only concern is to decide where I should place the sensor, right? And also probably what is the shape of the sensor, whether it should be a square sensor or a circular sensor. Okay? So now how do I measure the quality of this sensor? Well, in fact, our criterion will be very elementary. It will be to say, okay, assuming the inequality is true. Of course, if the inequality is true, this sensor is not good, so I will ignore it. If the sensor is good enough so that the inequality is true, the size of the constant C over there will be a measure of the quality of the sensor. Of course, the smaller is this constant here, reversing the constant on the left, this will make a big constant there. It means that by making measurements in a small omega, I am capturing a big fraction of the total energy of the solutions. By the contrary, if the constant is nearly infinity, it will mean that, this sensor is very, very weak, is very poor. So what I am considering now as problem is that of minimizing this constant C on the observation zone, right? So this is, if you want to, this can be thought as being an optimal design problem, that of within the class of solutions of this wave PDE in capital omega, find the set small omega with a given volume fraction, say 10%. I like to occupy only 10% or 1% of the domain with the sensors. I don't want a monster sensor which is occupying the whole space, because otherwise there will not be seats for us, right? So given the measure of the sensor location small omega, try to minimize this constant. Okay, so, well, when you think on this, well, of course, this is the linear wave equation, constant coefficient. The best, the first thing you can try is Fourier expansion, right? So these are the eigenfunctions of the Laplacian, everyone knows. The Laplacian, the Dirichlet Laplacian in the domain omega has a very nice spectrum. So I decompose the solutions of the wave equation on this eigenfunction basis. In time, I have these sinusoidal responses, exponential square root of lambda kt, of course with an I, they are trigonometric functions, right? And then I try to realize how much energy I am recovering in small omega. So I have to take this integral of the square, then I get a double sum, and then you see that in this double sum, in particular, there is this red term. This red term is the integral of, in small omega, of the cross product of the eigenfunctions phi k, phi j. Okay, not so bad. So now, there are a few warnings, though, about the eigenfunctions. So, of course, the eigenfunctions of the Laplacian are a beautiful object. We all know for any domain, they will produce an orthonormal basis of L2 or H10. So they are great. But our intuition is very much limited to 1D. We have a very little intuition about how eigenfunctions behave in multi-D. Of course, explicit computations are impossible in general. And even numerical effective computations of eigenfunctions beyond the 20th or the 50th will be very difficult to perform. Actually, let me also remind you that this was, I think, if I understand correctly, this was the origin of the domain decomposition method. So Hermann Schwarz, more than 100 years ago, he was struggling about how to compute the eigenfunctions of the Laplacian in this very naive domain, which is the union of the superposition of the disk and the rectangle. Of course, he knew the eigenfunctions on the rectangle, right? Separation of variables. He knew also the eigenfunction on the disk. So these are radially, radial polar coordinates. Now the question is how you do it in multi-D, in this multi-domain. And he soon realized that this will be impossible. And he derived the alternating, the splitting, the domain decomposition method as a way of approximating the solutions in that domain. So we have to be very careful, because even though this seems to be a very natural analytic approach, this is impossible in practice. So actually, we consider that problem as being impossible in the sense that it was impossible for us, right? Because we have very little information on these cross products when you are in a small omega, okay? Of course, this will be the Kronecker delta if you were integrating in capital omega, but the understanding of the quality of the sensor location, small omega, requires manipulating these cross products in small omega. And this is something that can be very, very, very wild, right? So what you do when a problem is very difficult, then you put some fog, right? So let's make the problem disappear, right? So if I am not able to solve it, let me simply ignore it. So let us put some fog. Let's do some mixing on this problem, which is actually, I think, the spirit also of these very successful GAMM conferences. So there are two ways of mixing. One is infinite time. Well, it's true. I mean, from an engineering practical point of view, infinite time is maybe too long, right? It's true, but still, from an analysis point of view, it makes sense. If you do this observation in a time horizon, which is getting longer and longer and longer, and then you average, when passing to the limit, you see that the cross terms disappear. This is simply because of the orthogonality property of complex exponentials in time. You don't need to use any information on the eigenfunctions. They simply, due to the orthogonality in time of these trigonometric functions, all the cross terms will disappear, and this will become the Kronecker delta. There is maybe a more smart way of mixing, right? So this was this lemma is attributed to Zygmunt, and indeed is in the book of Calderon-Zygmunt. But, well, in fact, in the book of Calderon-Zygmunt, there is so much, right, that probability is almost 1. And this issue has been, these kind of ideas have been developed very deeply in recent years by Nicolas Burke and many other collaborators, so that in order to go beyond the typical critical exponents for the solvability of PDEs, right, for nonlinear PDEs, there are critical exponents that are very often related to Sobolev embedding. They said, okay, let me mix, and then I will go forward. I will simply be able to break down this threshold. Let me explain you how this works at this level. So the idea of Zygmunt was very simple. Go back to this, say, Fourier series, okay? So we all know the Parseval identity. Given the coefficients in little L2, you have a function in L2 of a space. And then there is a pure isometry, little L2, L2, Fourier transform. Right? So what Zygmunt said is, he said, let me put here the sign, let me modify the sign of this coefficient at random, right? So put -1 to the power mu k, mu given by some kind of, for instance, Bernoulli distribution. Let me randomize the sign, right? And then compute averages. It turns out that the Sobolev embedding theorems for randomized, when you look to the expectation of the randomized, say, functions you obtain, the Sobolev embeddings are improved, and the same happens here. When you look to the expectation of the observed quantity, rather than the observed quantity itself, you mix waves. Now, by switching signs, and then you take expectation, now randomization occurs, and the cross terms vanish. So in this way, either by randomization or by infinite time, you go back to this, say, inequality, in which now you see I'm not missing anything. The cross terms simply disappeared, right? So the point I'm making then is that this original problem was impossible for us because of these cross terms. Now there are two ways of randomizing, either letting time go to infinity or randomizing in the Zygmunt spirit, and then you can get to an inequality which is purely diagonal. Okay, so we now feel much more comfortable. It's just a matter of taking the eigenfunctions, square the eigenfunctions, measure the eigenfunctions in little omega, and now look to the constant in this inequality. Okay, so again, now the problem becomes minimize this constant among the class of admissible possible locations and shapes for the sensors, omega being a set in capital omega of a given size, of course, less than the total domain capital omega. Well, maybe before getting to this, as you will see, difficult problem, as a preparation, I will consider a simpler one, right? Which is not of very much practical use, is what happens when you are only measuring one single wave. Well, if you are simply measuring one single wave, right, then, of course, the optimal location of the sensor will be like a polar cap, right? It will be a level set, will be given by level sets. So, but you see that already at that level, there are some subtleties from an analytical point of view. Actually, the results, you can, I mean, this is not very difficult to do, is simply mastering Fourier series in 1D carefully. You can prove the following. You can prove that if the initial data of the wave equation you are considering are analytic, right, then the solution is analytic. Then because of the solution being analytic, if you take these polar caps, you simply cut, say, the level set to determine that the optimal location of the sensor will be this piece plus this piece, because this is the one that is capturing most of the energy. Generally speaking, if the solutions you are dealing with are analytic, you can prove the optimal sensor is given by a finite number of say, connected components, which is nice, right? So it means that, well, maybe you need to cut your sensor in several pieces, but the number of pieces is finite. Now, as soon as you quit, and at this level we use the classical results by Mandelbrot on this, back in 1934, right? So this was the time of Hardy and all these people. Palais Wiener and so on. They were probably all together, I don't remember. No, this one was in France, I think. Yeah, Bulletin de la Société Mathématique de France. Now, but as soon as you quit analyticity, of course, surprises arise, and then there are say infinity initial data for which the optimal sensor is a Cantor set. Well, it's still a set, right? But you have to make it Cantor, which is a bit inconvenient. So you have to take your sensor, carry it in an infinite number of pieces as Cantor, and then place it in a very strategic manner in your chamber. Okay? Now, this is an interesting question because, you see, I have taken these simulations, not very sophisticated for GAMM, I know, I'm sorry, right? This was actually done in our personal computer using IPOpt, which to a large extent is a German project, I think. Interior penalty optimization, you can freely download, and it will optimize everything better than you will be able to do it yourself by any kind of, say, gradient-like algorithm. So when you do numerical simulations, you always see pictures like this. And then people in the articles before us, they were reporting, you see, there is relaxation. And actually, not always. As you will see, there are relaxation phenomena, indeed, related to these problems, but this is not the case in this one. So there are, say, infinity initial data for which the optimal set is a Cantor set. So I should say that in our case, there is no relaxation, there is Cantorization. The problem is that it's very hard to distinguish by, say, human observation whether it's going to be a Cantorization procedure or a relaxation process. So what is Cantorization means? The optimal set is a Cantor set. What is a relaxation? Relaxation means there is not an optimal set anymore. The optimal set in the weak limit becomes a density function, a continuous, absolutely continuous density function, okay? But this is, you agree with me that by doing numerical simulations, you will have to be very, very smart to distinguish between Cantorization and relaxation. But there are relaxation phenomena, indeed. Now, let me go back to the original criterion. The original criterion was not dealing with one possible wave, because if I know the wave, I don't even need to measure it, right? So the problem until now was an exercise. Now, assume I don't have any clue of what the wave is. I am considering all possible frequencies, all possible eigenfunctions. This was already observed in a paper by Ebrard and Angot back in 2005. They said, relaxation occurs. You are looking for an optimal location of the sensor, there is no. The sensor has to be distributed everywhere in your domain, occupying the volume fraction given by, say, the number capital L. Of course, except in the particular case where the volume is half, in which case you could say, I place the sensor to the left or to the right. But in general, if you are given any other number, the sensor tends to homogenize, disseminate everywhere in the domain. The second observation, which is even more dramatic from a numerical analysis point of view, is that you say, okay, so Enrique, we understand. I mean, there are many oscillations, the sensor is getting distributed everywhere. But, here we are in an applied math conference, so we are interested on, say, 37 eigenfunctions. Okay, fine. So you take the optimal location of the sensor for the 37 eigenfunctions. And now you try to check how good it is for the 38th. It turns out that the optimal choice for the first 37 is the worst possible for the 38. So it means there is very little robustness. There is a lot of oscillation built in this method, even if you try to avoid the high frequency problem. But there is no gap. This is a true relaxation. So considering location for measures or considering the location for sets is the same. I have done a quasi-simulation for you. Let me see if it works, in which I try to explain why this occurs. So this is 1D, right? And you see here the square of the first eigenfunction in black. If you are interested only on the observation of one eigenfunction and you are given a volume fraction, say, of the order of 1/3, you agree with me that you will place the sensor in this blue patch in the middle, right? Because this is where the most amplitude, the energy of the eigenfunction is being captured. Okay, now let me consider the second eigenfunction. Now the second eigenfunction, the square, is in blue here, and you see the maxes of this function are outside. And precisely the location of the sensor for the first one, the middle one, is precisely the region where the second eigenfunction is very low, right? So it's very bad. So what is the best compromise for this two eigenfunctions? Well, the best compromise is doing this. You split the patch into two, and then you move them a little bit away from the center, not too much, right? Because you want the steel to be good for the first one, but approaching them to the maxima of the second one. And now you draw the third one, and you see, well, the third one is escaping again, right? So if you try to improve this second trial, then you will get to this. And if you continue, of course, you get to the relaxation phenomena. Now, this is true in 1D, but in 1D we know that the square of the sine kx converges weakly to 1 over 2, right? So this is the first exercise we all remember when learning about weak convergence, right? So this is the prototypical example. So this is our intuition in 1D. We will very much like that this is true also in multi-D, but unfortunately, or fortunately, depends, this is not the case. So already at the disk, you know, acoustic waves on the disk, when you look to eigenfunctions can be concentrated near the boundary. This is the well-known and well-experienced whispering gallery phenomena. And this is related to the fact that there is a ray of geometric optics, right, the green one, which is stable. You perturb it a little bit and it remains always turning around the boundary. And this pushes the existence of eigenfunctions of the Laplacian that are very much concentrated near the boundary, and for which the limit of this process will be something like a Dirac delta over the boundary, nothing equidistributed inside. So what is known about the eigenfunctions in multi-D? Well, this is a huge topic, right? This is a huge topic. Also for graphs by now, right? So domains, graphs, spectral analysis, high frequency behavior, rays propagation. This is a huge topic. But there are some classical results that are by now well known. The first one is that the Cesaro means do behave as we think. So our intuition is 1D. Our intuition is wrong in multi-D, but not so much. Cesaro said, if you do averaging, then it's still true. The average of a square of eigenfunctions converges to the constant density. And this suffices to show you that, well, the sensor that is spread everywhere is always a good solution, right? But still, we would like to know whether there are classical solutions. Now, you go back to the literature on the behavior of the spectrum and the link with the dynamics of the billiard, and there is this celebrated result by Schnirelmann, then continued by many others, that says if the billiard is ergodic, right, in the sense that all rays of the billiard have the tendency to fill out the domain everywhere, then most of the eigenfunctions behave as we like this. But only most of them. There is still a set, right, of zero volume fraction that, could hide some other artifacts, right? And then I would like to emphasize that our intuition that, for instance, in the domain omega, the rectangle, eigenfunctions are like this. And then they are bounded in L infinity, right? So this is a miracle for the rectangle. You normalize the eigenfunctions in L2, and they are also bounded in L infinity. This is, of course, not true in several space dimensions for general domains in general. So the best estimates we know about this are the so-called Soge-Smith projection estimates, and they are in between this very obvious L infinity bound and what the Sobolev embedding will tell you. But this is also a delicate issue. So actually, in multi-D, very little is known, right? So we know the density, the constant density is optimal, but if you ask, what about the real optimal set, very, very little is known. There is this conjecture, this is called, I think, the Barnett set, so this kind of concave rectangle in which people conjecture that this quantum unique ergodicity property is fulfilled, meaning that people think that in this set, all eigenfunctions homogenize to the constant. But so far, there is no proof of this result. And then, if you do numerics, right, you do again the same numerics as before, as I was doing in 1D, you increase the number of frequencies, and you see the tendency to homogenization. Except in some particular cases, like this, right? But this is due to symmetry. So this is the case of the square, volume fraction 1/2. So you have to place a sensor. There are some sensors that are optimal. So, for instance, this blue one, and they are all performing the same. You see, I am simply playing with the symmetry. You can think on this rectangle as extended periodically, and you will see they are all part of the same kind of construction. So all these sets are optimal. But this is only for the rectangle, and in this very particular case where the volume fraction is 1/2, right? So now, being in Italy, I thought that maybe this is not a very politically correct figure, right? Because someone could have some thoughts about football. It was not in my mind. But in any case, in order to avoid, I show you also some nearly optimal shapes. No? Okay, so now, still, we stick to our intuition that, well, all these issues about high frequencies should not matter so much in practice. And this is true to some extent. If you develop the same exercise for the heat equation, right? I don't even write it. We all know the heat equation. Of course, there is a lot of dissipation on the high frequencies. Then your intuition is right. Everything is driven by a finite number of eigenfunctions, and then you see how the numerical simulations stabilize very soon. So in this case, I have considered one eigenfunction. Of course, the sensor is in the center. Two eigenfunctions. The optimal sensor likes to do that. Three eigenfunctions, and after four eigenfunctions, you don't see any difference. So it's true that all the pathologies I was describing is very much related to wave phenomena. And in wave phenomena, all these things occur because high frequencies and low frequencies count the same. For heat processes where the world is very much unbalanced because the high frequencies are strongly damped, right? Low frequencies govern and they give you the optimal location. So if you now ask me, maybe you could ask me, what is the optimal thermometer? Well, this is the optimal thermometer. Okay, heterogeneous media. So far I was talking about the Laplacian, the wave equation with constant coefficient. Let me put variable coefficients. So for people that are used to deal with maybe parabolic or elliptic problems, well, this is not a big deal, right? Because we know that measurable, bounded, coercive coefficients, positive, they lead to the same theory as smooth ones, right? But this is not the case for wave equations. So just a few keywords about what's going on with variable coefficients. So the first principle is that if the coefficients are smooth, waves are still driven by bicharacteristic rays. But of course, rays are adapted to the topography, are adapted to the metric that these coefficients are given, right? Now, when the medium lacks regularity, for instance, if you have some cliffs on the coefficients, some discontinuities, or some very rapid oscillations, you may have resonance phenomena. You may have waves that are trapped in the middle without ever propagating towards the boundary, right? So our intuition is very much related to a smooth media, breaks down when the coefficients are non-smooth. Right? Now, going back to a smooth media, so that our intuition, is okay and everything is driven by bicharacteristics, what may happen is that even when bicharacteristics are there to drive the energy, the bicharacteristics can be trapped, right? And this is, for instance, what happens in the velodrome, right? So it was good to work in this topic because I finally understood why the velodrome is that way, right? So it's a strange construction, right? Why people like to bike. Biking is great. By biking in a velodrome with such a slope, such an unstable configuration, this is precisely to produce a loop, right? So this is a bicharacteristic ray that is turning around again and again and again. And actually you can prove that if you take a wave equation that way, they take, for instance, density 1 and take sigma, which is parabolic on a given, say, tubular region, then you can build a bicharacteristic ray which is turning around in a closed cycle, as in the velodrome, right? So meaning that even if waves are driven by bicharacteristics, the dynamics of the billiard, because of this change on the geometry, changes also dramatically. So our intuition often fails. And this is, of course, very much related to a very hot topic about cloaking, metamaterials, and invisibility, where, well, in the context of control and observation, of course, we want to see things, right? The goal of these people was the opposite one, right? Not to see anything, to hide, right? But this is part of the same, so two sides of the same phenomena. Well, for non-smooth media, as I said, waves can get trapped. When waves get trapped, the only thing you can do from a control theoretical point of view is make your controller move. This is the only thing you can do, right? So if waves don't get to you, you go to the search of the wave, right? So this is the vacuum cleaner strategy, right? Okay, so numerics. Well, we were dealing with constant wave equation, variable coefficient wave equation. Now we go to numerics. We are doing numerics. I'm thinking mainly on finite differences, although everything I'm saying applies also to finite elements to some extent. I will explain also the limitations. Of course, in general, we would like to, in order to face realistic applications, something that I will not do, we will need to deal with measures that are irregular. And from what we have learned in the past slide about waves in heterogeneous media, we can already start guessing that maybe if you are putting some irregularity, some heterogeneity on the mesh, then maybe you will be producing some numerical artifacts that are not totally expected. Okay, let me explain you this. So this is, again, we go back to 1D. Constant or variable coefficients. So this is irrelevant at present. So the key point here will be numerics. So this is, again, a generalization of D'Alembert. You have a nice energy which is conserved. Now I do numerics, right? And the first chapter of numerics will be finite differences on a uniform grid, right? A grid like in here, a uniform mesh. But let me move to the second chapter, right? The second chapter is about finite difference approximation in non-uniform meshes. So how do I do that? Well, I take a map, G, which is going to be a smooth, back and forth, a change of variables, and I map this uniform mesh into a non-uniform mesh. Okay, fine. I can still write down, if you are careful enough, you will find this, say, finite difference numerical scheme. It is conservative. And it converges in the classical sense of numerical analysis. So there is nothing bad. It's the same, it's as good, this scheme in this non-uniform mesh, as the one you all think of by a three-diagonal discretization of the Laplacian with an N matrix, right? A Topliss matrix. It's as good, this one, as the classical one for the constant coefficient wave equation in a uniform mesh. Okay, so we started playing with this and we realized that, as Fermat said, this problem is not one of the easiest, right? This is what Fermat said when he was not able to prove the Snell principle for the refraction of light. This problem is not one of the easiest. Then we realized that very probably in order to understand what's going on, we should go back to the theory of rays, right? So in order to do that, we need to define a symbol for this numerical wave operator. Well, the way you do it, you see, in the Fourier space, we are doing something very, very standard, the von Neumann analysis. Xi squared for the symbol of the Laplacian becomes 4 times sinusoidal square of Xi over 2. There should be some H over there for the mesh size if you scale everything to the mesh. But the key point here is that, there is an effect due to the change of the mesh. So you see that in some sense in this symbol, and this is why I'm writing down explicitly the symbol for you, you see that the fact that the mesh is not uniform anymore, right? Gx is not x, is not the identity, so G prime is not constant. The effect this has on the numerical scheme is the same as a variable coefficient and heterogeneous medium for the propagation of continuous waves. Okay, out of this Hamiltonian, you can build a bicharacteristic system, and then you can analyze how waves develop. Okay, so this is an ODE to be solved. I mean, this looks a bit complicated, but after all, it's a Hamiltonian system. This gives you a billiard, right? But now the billiard is associated to this numerical mesh, right? Which is non-uniform, as in here. So what is the effect of this numerical mesh on this numerical billiard? Okay, there is, of course, theory for this, right? So you can formulate this using Wigner measures, as done in the papers by Markovic, Gerard, Poupeau, also Lyons-Paul. There is a huge literature on Wigner measures in order to, say, avoid these explicit or quasi-explicit geometric optics constructions, right? But you could also do it by these kind of tools if you prefer to, right? There is this classical works by Wisniewski, for instance, on this topic. Okay, let me again explain you what was going on by a quasi-numerical simulation. So what I will show you here is the following. So here in the lower right corner, you will see the dynamics associated to the Hamiltonian system. So this is the dynamics of the rays. So dynamics in space, right, and time, right? So this is a space on the horizontal, time in the vertical. So you see there are 3 different simulations. In all of them, you will see a wave emerging from the center of the space interval, right? So this will be a wave packet. And the only thing I'm doing is I am putting a Gaussian envelope on this wave packet, and I am making it to be higher and higher frequency on oscillations, okay? So now what I'm describing here is what is the behavior of the corresponding ray of this, say, numerical Hamiltonian system, of the numerical billiard, right? And here I am plotting what MATLAB is, so I am really plotting the solution you obtain by doing a numerical simulation. So I am trying to compare the finite difference PDE simulation with the behavior of the rays. And this is what you see. Okay, so it's clear, right? Okay, so what does it mean? So I like this wave, right? Because this wave is getting to the boundary and is bouncing back. This is what the D'Alembert equation does, right? So this is good. This is all right. And this is due to the fact that this corresponds to this purple dot, right? In the bicharacteristic Hamiltonian system, this purple dot is going much away the boundary of the domain, so it's bouncing back. But there are waves, for instance, this one, this is a very strange wave. So the wave is departing from here, should get to the boundary and bounce back. And this numerical wave, which is a true numerical solution of the problem, decides to come back before getting to the end. And this is due to the fact that for this, so this is the blue dot, in this Hamiltonian system, the corresponding trajectory is a periodic orbit which never touches the boundary. And then you can exaggerate this fact by, for instance, building a wave which is almost a standing wave. There is a small vibration, but the wave almost stays on a perpendicular vertical tube. And this is due to the fact that, in this case, this is a fixed point for the billiard, for the numerical billiard. You see, this and these are totally fake waves, which are produced by the fact that the grid is heterogeneous. Well, it took us a long time to understand this. And once I was in an engineering conference in the Netherlands explaining this, and someone in the lecture room told me, well, Enrique, this is obvious, right? Why? You see, so here the grid is heterogeneous. I am taking a wave which is very narrow, very small, say, wavelength, very high frequency, right? And this wave, because of being so narrow, needs a very narrow mesh to live. So in this simulation, the mesh is getting coarser and coarser when approaching the boundary. And this is why this wave, that needs to live in a very narrow medium to survive, right? When approaching the boundary where the mesh is getting too coarse, because, I mean, there is no life there for the wave decides to come back. So it's actually a very human behavior, right? Now you can do it in 2D. You take I think in this case are finite elements, say rectangular finite elements, triangular finite elements. I simply, pull, the geometry of the mesh a little bit to make it coarser on the boundary, and this is what the rays do, right? You could do numerical simulations for this, and you will see what this video of the numerical rays are exhibiting. So the numerical rays stay in these very chaotical, totally no-sense trajectories, right, without ever getting to the boundary. Well, once you see this, you can also design the remedies. And this is a recent work we did with Silvana Hervedoza in Toulouse and Aurora Marica. What we learn now is that, well, if you were about to place the sensor on the right, then you have to make the mesh getting finer and finer when approaching the sensor. Why? Because then you will not avoid that the numerical waves return without getting to the LED boundary, but then you will make sure that all numerical waves are getting to the sensor location. So this also gives you a hint, the analysis of these numerical billiards give you a hint of how to shape the grid so to preserve the inverse, say, problems property for the PDE. Well, the conclusion is mainly that this is a fascinating topic. There there is plenty to be done, in particular in the multidimensional case, both from the analysis and from the numerical analysis point of view. From the analysis point of view, this belongs really to the community of people doing spectral theory and dynamical system theory for billiards. In the numerical analysis community, I think there is plenty to be done in multi-D to understand how shapes of grids affect the propagation of waves, and there is a problem that is totally by now out of reach, is the one in which the grid deformation is not smooth enough. So as you have seen, you remember, in my grid deformation, the diffeomorphism needed to be C2, C11. If you give me a grid that has been deformed by, say, Lipschitz diffeomorphism or something like this, then our analysis fails because of the lack of regularity. Thank you.